Okay. Hi, everyone. My name is Edmond Cheung, and I'm a postdoc at the Kavli IPMU in Japan. And today I'll be presenting a project that I've been leading in the manga survey, which is in collaboration with Kevin Bundy, these folks, and the rest of the manga team. This work introduces a new class of galaxies called the Red Geysers, and they represent new evidence for AGN maintenance mode feedback. So, what are red geysers? Well, here are three examples of red geysers, and while they appear to be unremarkable elliptical galaxies in their color composite images, they become quite remarkable upon inspection of their H-alpha equivalent width map, H-alpha equivalent width maps, which is shown in the right column here, and where lighter spaxels represent more H-alpha emission relative to the stars. Now, what's intriguing about these maps is the narrow bisymmetric pattern that extends across these galaxies and is not evident in the color composite images. So the question is, what's causing these patterns? To answer that question, let's focus on this red geyser in the middle, which is interacting with another galaxy to its left. They are separated by 32 kiloparsecs, and they're not part of a larger group. Manga has observed both these galaxies with two hexagonal bundles of fibers, as outlined in the hexagons. And, well, here are their color composite images, which we've nicknamed Akhira and Tetsuo. So how does Akhira and Tetsuo compare to the current manga sample, the adopted manga sample? Well, here is the res frame NUV minus R color mass diagram of the adopted manga sample. And here is where Akhira and Tetsuo lie. And as you can see, Akhira has a moderate stellar mass with a very red color, meaning that it is a typical quiescent galaxy. Now, being a typical quiescent galaxy, Akhira displays no substantial star formation. However, despite the lack of star formation, Akhira does display extensive ionized gas, as you can see here in its H-alpha flux map, and where darker spaxels represents more H-alpha flux. And as I showed earlier, the most intriguing aspect of Akhira is this narrow bisymmetric pattern that extends across the entire galaxy in its H-alpha equivalent width map. So, since there is no star formation in Akhira, it's not obvious what this H-alpha traces. But we can begin to answer this question by examining the ionized gas velocity field, which I show here in the bottom panel. And as you can see, there's a large gradient that goes from plus minus 300 kilometers per second. Now, velocity fields such as this have been commonly interpreted to be from rotating disks. But for Akhira and the rest of the red geysers, we find the disk interpretation to be unsatisfactory for the following reasons. First, the ionized gas velocity field is very different from the stellar velocity field, which is shown in the upper panel. As I said, the ionized gas velocities range from plus minus 300 kilometers per second, whereas the stellar velocities only range from plus minus 20 kilometers per second. And moreover, the position angles of these two velocity fields are offset by about 25 degrees. Also, we find that the ionized gas velocity dispersion map is much more complicated than the stellar velocity dispersion map, especially this large knot to the left. And while the stellar velocity dispersion map is smooth and symmetric, the ionized gas velocity dispersion map is quite asymmetric. Now, what all these discrepancies indicate is that the ionized gas is decoupled from the stars. But the key argument against the disk interpretation is from dynamic modeling. So, using the stellar dynamics of Akhira, we are able to model the gravitational potential of Akhira using the Jeans anisotropic modeling technique, i.e. JAM. And with this gravitational potential and a detailed description of the H-alpha surface brightness map, we are able to predict the second velocity moments of the ionized gas, i.e. VRMS, which is defined to be the quadrature sum of the ionized gas velocities and the ionized gas velocity dispersions. And from Galfit fits of the H-alpha flux map, we find that the best fitting gas inclination is about 46 degrees, which predicts these second velocity moments across the major kinematic axis. And here are the predicted second velocity moments, assuming the most extreme inclination of 90 degrees, i.e. edge on. Now, taking the observed ionized gas velocities across the major kinematic axis, as shown by these spaxels, and the observed ionized gas velocity dispersions across the same major kinematic axis, and then summing them in quadrature gives you the observed second velocity moments, which, as you can see, the observed second velocity moments far exceeds the predicted second velocity moments, indicating that the ionized gas is not moving under the influence of gravity alone. So instead of a disk of ionized gas, we favor an outflowing wind of ionized gas with a wide opening angle. This wind model can reproduce many of the qualitative features of the data, including the ionized gas velocities and the ionized gas velocity dispersions. And here is a schematic diagram of our wind model, with the gold ellipsoid representing Akhira and is consistent with the JAM modeling. The wind, the purple cones represents the wide-angled ionized wind, and the inner green cone represents the central, more concentrated portion of the wind. Now, in addition to being able to reproduce many of the qualitative features of the data, this wind model can also explain this narrow bisymmetric H-alpha equivalent width pattern through shocks and or overdensities in the central cone of the wind. And in fact, wind-driven shocks are consistent with the line ratios in Akhira. So here is the BPT diagram, O3 over H beta versus S2 over H alpha, of all the spaxels in Akhira that have signal-to-noise greater than 5 in all these lines. And below is the resolved BPT diagram, where every spaxel is color-coded according to its location in the BPT diagram above. And as you can see, the majority, almost all the spaxels in Akhira display liner line ratios. And according to Atlas 3D, recent work by Atlas 3D and others, liner line ratios in early type galaxies are most likely generated by evolved stars. However, since Akhira has an outflowing wind of ionized gas, shocks are likely an additional source of ionization. And we believe we see evidence of these shocks in this narrow H-alpha equivalent width pattern that is oriented along the ionized gas velocity field. Now we can test for the possibility of shocks by comparing the line ratios within this H-alpha equivalent width pattern to line ratios predicted by fast shocks. So let's first outline this H-alpha equivalent width pattern onto this resolved BPT diagram right there. And let's pick out some spaxels within this H-alpha equivalent width pattern and see where it lies on the BPT diagram above. Now we can overplot a fast shock model from Allen et al. 2008, where the peach-colored lines represents shock velocity and the light blue lines represents magnetic field. And what you can see is that the line ratios within this H-alpha equivalent width pattern are consistent with the line ratios predicted by a fast shock of around 300 kilometers per second, which is similar to the observed ionized gas velocities, the maximum observed ionized gas velocities that we see in the data. Now, in support of the presence of shocks, line ratio maps of O3 over H beta and S2 over H alpha display complicated and irregular structures, similar to the ionized gas velocity dispersion map, which is indicative of a tumultuous and multi-component ISM that is consistent with the presence of wind-driven shocks. So, having argued for the presence of an outflowing wind, the natural question is then what could be powering this wind? Well, the detection of a central radial point source and a lack of star formation strongly implies that there is an AGN in this galaxy, which could very well be the power source of this wind. Follow-up Jansky VLA observations with much higher resolution, 1.5 arcseconds, confirms that this radial source is indeed a central radial point source, meaning that this AGN feedback is not manifested in extended jets. Instead, it could be in the form of small-scale jets, less than 1 kiloparsecs, or uncollimated winds that are predicted to occur in AGNs that are powered by low accretion rates and or radiatively inefficient accretion flows. And this latter possibility is intriguing because the Eddington ratio of this AGN is only 10 to the negative 4, meaning that accretion onto this AGN is at a low rate and or radiatively inefficient. Now, this type of AGN has gone by many names, which has been mentioned already today, like radio mode, jet mode, kinetic mode, and maintenance mode. And AGN maintenance mode is predicted to suppress star formation in galaxies, in particular quiescent galaxies. So is there any evidence that star formation is being suppressed in Akhira? Well, the answer is yes. As I've shown throughout the talk, Akhira is interacting with another galaxy to its left, Tetsuo. And according to merger simulations, which we run, Tetsuo should be depositing some cool material onto Akhira at this point of the interaction. And we see evidence of this cool gas deposition in the sodium D doublet absorption lines, which are probes of the cool ISM. So here is the sodium D doublet equivalent width map, where darker spaxels represents more absorption. And you can see that there is strong spatially asymmetric absorption on the right side of Akhira. And since the stellar distribution of Akhira is smooth and symmetric, this irregular absorption is most likely due to cool material in front of Akhira, which is consistent with the dust extinction map, measured dust extinction map. Now we can determine whether this cool material is flowing into or out of Akhira by measuring the line of sight velocities of this cool material, which we've done and show here on the right, where red represents cool material that is redshifted with respect to Akhira, and blue material that is blue shifted. Now, since the majority of this cool material is redshifted, we conclude that this is an inflow of cool material likely deposited by this interaction. We can take this analysis one step further and estimate a gas mass using the dust extinction map and a dust-to-gas ratio. And then with this gas mass, we can estimate the expected star formation rates using the Kenneket-Schmidt law, which turns out to be about 10 to the negative 2 solar masses per year. But the measured star formation rate of Akhira, which is based on SED fitting of optical and infrared photometry from SDSS and WISE, is only 10 to the negative 5 solar masses per year, much less than what is expected given this amount of cool material. So why is Akhira still quiescent? Well, we find that the power of this AGN-driven wind is about 10 to the 39 ergs per second, while the cooling rate of the ionized gas is about 10 to the 38 ergs per second, and the cooling rate of the cool gas is about 10 to the 39 ergs per second. Thus, this AGN-driven wind can balance the cooling of gas within Akhira, meaning that this AGN feedback can suppress star formation and maintain Akhira's quiescence. And since the rest of the red geysers show similar properties, we believe they're all experiencing AGN-driven winds, which could represent how typical quiescent galaxies maintain their quiescence. Now, speaking of the rest of the red geysers, I will show you them all now. We have 26 in total. On the left is the color composite images. In the middle is the H-alpha equivalent width pattern. And on the right is the ionized gas velocity field. As I flip through these 26 red geysers, notice that the H-alpha equivalent width pattern is oriented along the ionized gas velocity field, similar to Akhira. And while I don't show the stellar velocity field, they are almost always oriented differently from the ionized gas velocities, and almost always with a different range of velocities. We call these galaxies red geysers because they're quiescent, making them red, and because we believe their AGN outbursts are episodic, like a geyser. We expect to find more as the Malga survey continues, and we're currently analyzing the rest of the sample. We also expect to find more of these. We also expect to find red geysers in other IFU surveys as well, like Atlas 3D, SAMI, and Khalifa. And in fact, we believe we have identified some of these red geysers already in these other surveys, and we look forward to examining them in more detail in the future. So here are the last 2 red geysers, and thank you for your attention.
This is great stuff. Any idea what's causing the orientation of this wide angle outflow? Is it oriented with respect to anything else that you see? That give us some clue as to the origin of the wide angle.
It's not correlated with axis ratio or, well, axis ratio specifically. And we believe these winds, these orientations are driven by the accretion disk orientation, which we can't resolve, obviously. So we assume it has to do with the AGN, but if we had better data and resolution, maybe we could get a handle on that.
Yeah, but an estimate of what fraction of the 26 show an interaction like the one you
Yes, none of them do, except Akhira. So we believe that the main source of gas is from stellar mass loss from evolved stars, which has been predicted by Chiadi et al. Over the years to be the major source of gas for quiescent galaxies. And as they have shown throughout these last few decades, you need some way to suppress the cooling flow that will happen from this gas mass, evolved gas mass loss. If you don't suppress this cooling flow, then star formation will occur. And we believe this AGN radio mode feedback maintenance mode is likely the answer. Well, I believe Chiari et al. Initially suspected that for low mass quiescent galaxies, the supernova 1A is enough to suppress the star formation rate and the cooling flows from this evolved gas stellar mass loss. But for the more luminous quiescent galaxies, which you expect more stellar mass loss from these evolved stars, the supernova 1A doesn't seem to be enough. And I think in their most current papers, 2010, they require an AGN maintenance mode. And I don't think the supernova 1A is consistent with the radiocentral point source that we find. It has to be either star formation or AGN. And since this is a quiescent galaxy, we strongly believe it's going to be from an AGN.
What distinguishes the red geysers from all the other quiescent galaxies? Why are they red geysers? It seems like you're talking about what happens to almost every galaxy.
Well, observationally, what distinguished them was this H-alpha equivalent width pattern. But I think in a typical life cycle of quiescent galaxies, you expect that 85% of the time the quiescent galaxy is slowly accumulating gas from stellar mass loss of evolved stars. And only a small fraction of a typical life cycle do you have a cooling flow in which you need AGN feedback to suppress the star formation. So we're currently working on another project that looks at the radio activity of these red geysers versus a control sample of quiescent galaxies to see if there is more radio activity versus in these red geysers versus a non-red geyser control sample. And right now it does appear to be that way. And the fraction that we find for the red geysers, about 10% of the quiescent population, is actually similar to the duty cycle predicted by Chiari et al. 2010's typical life cycle of a quiescent galaxy in which you need AGN feedback to suppress star formation. So it seems consistent.
All right, let's thank our speaker again.